displacement x, velocity v, and acceleration a can be summarized as follows. Well, in a simple language, we can summarize these like this. Is that right? We have x equal to vt if the velocity is uniform, and v equal to at if the acceleration is uniform. But these are very simple relations. Alright, we can now use calculus to represent these relations. You know, velocity is the derivative of the position function, v equal to dx over dt, where x is a function of time, x is the position function. And x therefore can be obtained by integrating the velocity function, x equal to integral v dt. Acceleration is the derivative of the velocity function. Alright, can you write a similar relation here? How can you obtain the velocity function if you know the acceleration function? Alright? Velocity function is obtained by integrating the acceleration function. Well, this is the summary of displacement x, velocity v, and acceleration a. And you must be familiar with this. It will be easier to solve problems this way. Now, we will now develop equations to describe uniformly accelerated motion. Alright? What is the meaning uniformly accelerated motion? Uniformly accelerated motion means that the acceleration remains a constant throughout motion. As I told you earlier, we will only deal with uniform acceleration in this case. So, we will now develop equations to describe uniformly accelerated motion. And to do that, we are going to use some notations. And let's put down some of these notations. When t equal to 0, we will assume that the object is at position x0. So x0 means the position of the object at t equal to 0. T equal to 0 is when we start our clock. So when we started the clock, where did you find the object? At x equal to x0. And what velocity did it have at that time? We will call that v0, v sub 0. So v0 is the velocity at t equal to 0, and the particle is at x equal to x0 at that time. Now, very often I have a habit of representing the v0 as v sub I. Now, if you see that, think that they are the same thing. What does v sub I stands for? Initial velocity. Initial, when you start your clock. Okay. It has a uniform acceleration a. In other words, the acceleration does not change. Its value is a at any given time t. So once again, we are going to look at a particle moving which is at the position x equal to x0 when t equal to 0, and at that time it has the velocity v0 and has a uniform acceleration a. After a time t, the position is x. X represents the position at any given time, and its velocity is v sub f. Final velocity. You see that? As I told you, very often I will use v sub I for v0. Initial velocity, final velocity. And I have also a habit. In place of v sub f, I will simply use v. V is the velocity at any given time, the final velocity. Alright. Let's develop the first equation of motion. The first equation of motion is actually the definition of acceleration. Do you recall the definition of acceleration? Well, acceleration is change in velocity divided by time. So this is going to involve the final velocity Vf, the initial velocity V0, the acceleration and time. What all you need to do is write down that equation for acceleration. Can you write down that equation for acceleration? Well, I got that down for you. A equal to change in velocity, final velocity minus the initial velocity divided by time. Well, rearrange this. Multiply both sides by t. I can write A times t equal to Vf minus V0, or rearrange that and we get this beautiful equation. Vf equal to V0 plus At. Final velocity equal to initial velocity plus acceleration multiplied by time. This is the first equation. What is the first equation? Vf equal to V0 plus At. Or I will simply sometimes say V equal to V0 plus At. Look at the second equation. The second equation, we are going to use the concept we developed earlier. Suppose you have an object that starts with an initial velocity V0. So I'm going to use a graph of velocity against time to develop the second equation. Alright, now listen carefully here. You have a particle initially having a velocity V0 and it has a uniform acceleration and it has a final velocity Vf, and that happened during a time interval t. Alright, now consider an object which has an initial velocity V0 moving with uniform acceleration a for a time period t seconds and attains a velocity Vf during that time. Now dc is the velocity time graph of that particle, is that right? And what does the area under the graph represent? What does the area enclosed by the graph with the time axis represent? It represents the position function. It represents the displacement. The displacement x of the object during this time t is given by the area under that graph. In other words, if you can now measure the area of this shape, OACD, the area of this figure, OACD, is a measure of the displacement of the object. Can you tell me what that area is? Well, let's look at that area. This area can be divided into two parts. It is made up of this rectangle and this triangle. So in order to obtain the total area, I need only write down the equation for the area of the rectangle and then the equation for the area of this triangle. Add them together, I get the total area. And what does the total area represent? It represents the displacement of the object or the particle. Alright, area of the rectangle OABD is OA multiplied by AB. Tell me, what does OA represent in this diagram? It is the time t. You see that? OA is the time t, and what does AB represent? AB is the same as OD, and that is equal to V0. So this will be V0 times t. This is V0, that is AB, multiplied by OA is your time t. So area of this rectangle is V0 times T. What is the area of the triangle DBC? What is the area of that triangle? Area of a triangle is 1/2 base multiplied by height. 1/2 base, what is the base of the triangle? Is T. What is the height of the triangle? The height of the triangle is, if you look at this length is VF, the final velocity. And this length is V0. Therefore, what is that length BC? That will be VF minus V0. So the area of this triangle is 1/2 of base, that is T, multiplied by height, that is VF minus V0. Okay. And that will be, look at the way I have modified it. Now, do you recognize I have used the red coloring here? This VF has been replaced by V0 plus AT. That is our first equation. VF equal to V0 plus AT. So the area of the triangle now is 1/2 T times V0 plus AT minus V0. Look at this. V0 and V0 will cancel. And that gives us 1/2 T multiplied by AT. And T multiplied makes it T squared. So that will be 1/2 AT squared. This is the area of that triangle. And the area of the rectangle is V0 multiplied by T. What is therefore the total area? The area of OACD is area of the rectangle plus the area of the triangle. What did we say the area of the rectangle is? V0 multiplied by T plus, what is the area of the triangle we just obtained? 1/2 AT squared. And again, look at another beautiful equation. X equal to V0T plus 1/2 AT squared. Well, this equation we got assuming that at t equal to 0, the particle is at the origin. If the particle at t equal to 0, if the particle is at some other position called x0, then you need to add that to this. If at t equal to 0, the object is at position x0, then the position function, the equation for x, the position or the displacement, can be written as x of t, x as a function of time, is x0 plus v0t plus 1/2 AT squared. And this is the second equation. The second equation is for the displacement of a moving particle, and in terms of the initial velocity, acceleration and time. And you see, very often x0 will be 0 because we can take the initial position to be the origin. But there are some cases where x0 will not be 0. So we will keep this form, although in most cases x0 will be 0. So how many equations do we have now? We have now two equations. What are they? Vf equal to V0 plus AT, the first equation. You notice that that equation does not contain displacement. The second equation, x of t equal to x0 plus v0t plus 1/2 AT squared. Now what is the quantity that is missing from this equation? This equation does not contain